All right. With our next speaker is Alex Borisov on Kirch topology.
Well, thank you, Mel, first of all, for giving me this opportunity to share my mathematics. And thank you all for listening. I want to start with a disclaimer. This is a theory that's very much in its infancy, and I expect a lot from it, but it's strange even for my taste. But this is what I like about it. So let me start with Kirch topology. And for us today will be positive integers. And the topology is given by these arithmetic progressions as the basic open sets. Just X congruent to A mod D, so full arithmetic progression, where there are two conditions. A and D are co-prime, and D is square free. So this appeared in 1969 paper by Alan Marshall Kirch in Monthly, a short two-page paper. Without the square free condition, this is Golomb topology that goes back to Morton Brown and independent is Solomon Golomb. It has some rather remarkable properties. It is Hausdorff, connected and locally connected. In comparison, Golomb topology is Hausdorff and connected, but not locally connected. Now, according to MassSciNet, Kirch's paper has been cited 31 times. First two citations were in 1970 and 2013. So we're talking about a paper that was effectively forgotten for 40 plus years. Here's a good way to think of Kirch topology if you like more abstract stuff. Just by taking remainder modulo p, you can embed n into product of z over pz for p prime. And for each factor, we can consider a topology that's almost discrete. So non-zero singletons are open, but zero is dense. If an open set contains zero, it's just the whole thing. Then we take the product topology, and then we restrict it to n. Now, just in case you started thinking about the Kirch topology is not metrizable, in fact, countable metric space cannot be connected. Fix a point, consider the distance to it as a continuous function. You can finish the rest. Instead of n, one can consider non-zero integers. And this can be generalized quite a bit. Clark, Lewis, Lockhart, and Pollock had a nice paper in 2019. They generalized it in particular to Dedekind domains. They were mostly concerned with Golomb topology, but they did Kirch topology as well. Now, here's my opinion. Kirch topology is not a topological curiosity, but a fundamental, quintessentially global number theoretic object. I have about 20 minutes to convince you of that. If not, at least I hope that you'll figure out why I'm unconcerned with some advanced imitators taking over my mathematics. So the Hausdorff property, it just means that any two not equal elements can be separated by open sets. So if A is not equal to B, just take prime P greater than both of them. And X cannot be congruent both to A and to B, so they are separated. This theorem goes back to Kirch. Those sets that I started with, the basic open sets, they are in fact connected. And that includes the whole thing. U11 is just the whole n. It's a simple exercise. The main idea is if you take a closure of one of the arithmetic progressions, you get a bunch of arithmetic progressions, the set of all x that are congruent to 0 or A for all prime P dividing D. Well, you apply not to this U sub AD, but to smaller things. And it implies something that Clark, Lewis, Lockhart, and Pollock called Brown property in honor of Morton Brown. The intersection of closures of any two non-empty open sets is non-empty. In fact, it contains an arithmetic progression. I'm going to call these sets, the basic sets. And I want to point out connectivity is quite strong. Removing a subset of, say, natural or logarithmic density 0 from a basic set keeps it connected. Just to give you some feeling for what's going on, use of 1, 2, that's everything congruent to 1 mod 2, in other words, odd numbers. It's open, connected, and dense set. Here is another example. Seems like people haven't noticed it before because mostly people looking at Kirch topology were topologists. So together with my former student Sayaks and Gupta, I'm working on trying to generalize this simple observation. It's a difference in Gupta from a Ladi student whom he mentioned yesterday. The set of all squares is closed and connected, and its complement is connected. Connectedness of complement is because its density 0. It's connected because x-squared function is continuous in Kirch topology. And it's closed because if the number is not a square, then it's not a square modulo some prime. All right, here's the other side of the story. The title is the structure sheaf for Kirch topology. So what is a structure sheaf? If you have some topological space, a natural thing to do is to associate to every open set some set of functions that you are allowed to consider in this. A prototypical example is usual C with the usual topology and complex analytic functions. And this is actually something that I thought of slightly before I learned of Kirch topology, early 2024, inspired by work of the same Sayaks and Gupta, an iteration of integer polynomials. So I'm going to call these local integer polynomial functions, or lib functions for short. For any u, a subset of z, consider the ring of functions that have this property, well, they're functions to z, and have the property that on every finite subset, they are given by polynomial with integer coefficients. Equivalently, the interpolation polynomial is in z of x. So if some polynomial works, interpolation polynomial works. What kind of properties on the function does it give? If the set has just one element, that because we require the output to be in z, it's automatic. If the set is two elements, a and b, then it's a classical condition, the difference of inputs divides the difference of outputs. And you get more complicated conditions for bigger sets. So the starting point for everything here was this observation that there are actually quite a few of these functions. For infinite u, we have this inclusion, z inside z of x, then lib functions on z, then lib functions on u. This last inclusion is because the restriction of a lib function is lib, but more importantly, it's an injective homomorphism. In other words, a lib function is completely determined by its values on any infinite subset of inputs, which is a very simple thing to see based on this above example. Now, this theorem is almost longer to state than to prove. Suppose U is an infinite subset, U1, U2, and so on. Then the following constructions gives lib functions. Take any A0, A1, A2, and so on in Z, and consider A0, so a constant, plus A1 times x minus U1, plus A2 times x minus U1, x minus U2, plus and so on. At every step, you have AK times a polynomial, which is product x minus ui's for the first ki's. So it's a formally infinite sum, but for every element in U, it actually is 0 from some point on. So obviously, this gives a well-defined and, in fact, lib function. And it's easy to see that these a sub i's are completely determined by the values of the function, just by induction, and they're in Z if and only if the function is lib. So this is the bijection between those sequences and lib functions on mu. We call these expressions product sums. Here's a nice and kind of important example. Let's say A is less than D, and this is one of our basic sets, or really just any arithmetic progression. Then this construction gives us that every lib function is this sum, where you can kind of see what these factors are, right? If it's arithmetic progression, these appear a lot in combinatorics. And in general, product sums resemble power series, but especially for such U. We can define this sort of discrete derivative by taking f of x plus d minus f of x and dividing by d. It will go from lib to lib. And the derivative of the kth term is k times k minus first term. So this is just like for the usual power series and usual differentiation. All right, even though there's a word locally in lib, it's not a local object. Technically, it's a pre-sheaf rather than a sheaf. So we need to, what's called in algebraic geometry, sheafify it. If you haven't seen much of pre-sheaves and sheaves, don't worry, it's a very natural construction. Here it is. Suppose U is an open subset of N in Kirch topology, everything here in Kirch topology. Then a function from U to Z is called locally lib if for every element in U there is a neighborhood of it, on which the restriction of the function is lib. Basically, we're saying that for every A in U, the function is given as a product sum in some neighborhood of A. So it's just like complex analytic functions being given by conversion power series at some neighborhood of every point in the domain, which can be taken as a definition. So this is the sheaf that is on the title of the talk. And now I'm going to describe some of its properties. First of all, I like to think of this basic open sets as kind of building blocks. And this is the theorem: every locally lib function on a basic set is lib. It's completely elementary, but not completely trivial. It also generalizes to a union of pairwise intersecting basic sets. And there's this curious fact that if you have any finite collection of arithmetic progressions, if they intersect pairwise, then in fact they have a common intersection. We call these sets star-like sets. This is a schematic picture of a star-like set. The ovals are the basic sets, and they all intersect at some point. And now, how do you prove something like this? You start with a function which is locally lib. You assume it's not lib, and you get a contradiction. Now, what does it mean that the function is not lib? It means there is some finite subset on which the interpolation polynomial is not in Z of x. Naturally, we're considering smallest such subsets. We're going to call them circuits. The terminology is borrowed from the matrix theory. They in turn borrowed it from graph theory. So if a function is not lib, there is a circuit that kind of certifies that it's not a lib function. Here are some examples. Again, there are no circuits of size 1 because we require the values to be in Z. If we only require them to be, say, in Q, then yeah, there would be circuits of size 1. So circuits of size 2 whenever A minus B does not divide f of A minus f of B. And there are functions that say don't have circuits of size 2, but they have circuits of size 3. Like this function, 1/2 x minus 3 squared on odd integers. 135 is a circuit. It actually does not have circuits of size 2. Here's a simple lemma about circuits. Suppose X is a circuit. Then we know that by definition, interpolation polynomial is not in Z of X. But actually, we can say more. Its highest degree coefficient is not in Z. This coefficient has a name. It's called divided difference. It's used a lot in mathematics, especially actually applied mathematics. Suppose D is the denominator of this in simplest terms, then actually all elements of X are congruent modulo D. So the circuit must lie in some proper arithmetic progression. I want to say that arithmetic progressions are at the very heart of this whole subject. Now, here are some ingredients in the proof of this theorem that on basic sets, every locally lived function is lived. Circuit improvement lemma. This is a bit more complicated lemma, but still just a lemma. The hardest thing was to figure out that's what's needed. If x1 and so on, x sub n is a circuit, and we choose, say, first m of these elements, and if we have E in what I call convex arithmetic closure, which really is the smallest full arithmetic progression that contains x1 and so on xm, and E also has to be in a domain for f, then we can replace one of these x sub i's with E, and on the resulting set, the interpolation polynomial is still not in Z of x. Now, if you start with a circuit, you might not end up with a circuit, but if you start with a circuit of a smallest possible size, you will get a circuit. The same curious fact also comes into play. And another lemma. If you have a star-like set, and your function is lib on each of the u sub i's, then in fact it's lib in there on the entire u, on a union. And this helps to prove the theorem and also provides the generalization that I mentioned. So how does the proof goes basically? We suppose we have a locally lived function which is not lib. We get some circuit of smallest size, and then we improve it. We improve it to the point where for all x sub i's, the neighborhoods on which the function is lib must intersect. And then we apply the lemma and we get a contradiction. Now, this example goes beyond the star-like sets. And without 6n, it's a union of three basic sets, 1 mod 3, 1 mod 2, and 2 mod 3. So it's connected, open set in Kirch topology. It is not a star-like set. For a while, I wasn't sure if every locally lived function on this is lib. Now I know the answer, it's not. This is a fairly tricky theorem. One has to be careful. Basically, to grow counterexample from finite to infinite. In fact, the quotient is a rather mysterious and large Pro2 group. We do know it's torsion-free. My student Midun Vitil is working on this and related things for his thesis. The fact that it's Pro2 group has to do with the fact that if you have a locally lived function on this set, it may not be lib, but the only denominators allowed in the coefficients of interpolation polynomials are powers of 2. This theorem basically says, if you know Chekhov homology and some are familiar with sheaf theories, that we can calculate global sections or H0 of the lib sheaf on every open set U by Chekhov homology construction from the lib pre-sheaf. And the natural question, what about hierarchical homologies? This is a conjecture. So these basic building blocks are have no internal cohomology when it comes to coefficients in lib sheaf. Hierarchical homologies are 0. That would mean that they form what's called a Leray cover, also known as a good cover. So the answer to the above question is affirmative. It's still a conjecture, but I do know it for k equals 1. I know more. As a corollary of this, I know, for example, that H1 for this for our friend by now is 0, kind of because, well, these guys have no internal cohomology, H1. And if you look at this yellow picture, it's contractible. So in general, if the nerve of this cover is a tree, that's what you get. Now, here's a different animal, n without 15n. It's a union of 6 basic sets, 1 mod 3 and 2 mod 3, and 1, 2, 3, or 4 mod 5. And look, this seems to have an H1, and indeed, H1 is not 0, exactly for the reason you would expect while looking at this picture. I don't have a good feeling of this, I just know it's large because it's easy to get non-trivial elements. Okay, here are some ingredients of the proof that H1 is 0 for basic Q. This theorem is almost too strong, but it is true. If you have intersection of two open sets, the intersection, of course, is open. Actually, just openness of intersection is enough. And every lip function on V can be written as a difference of restrictions of lip functions on U and W. I want to emphasize this is true for lip functions, but not for local lip. Local lip may not be the difference of restrictions of local lip. But if V is such that every local lip function is lip, then this is very powerful too. Now, the real key to the proof was this definition. I call it a nest. We have a bunch of finite collection of basic sets U sub I and another collection of V sub i's. V sub i's pairwise intersect, so they form a star-like set. And U sub i's intersect with all V sub i's, and there's an extra condition. For any two x and y in a union of U's, if they're congruent modulo subprime, then there is V in a union of V's that congruent to the modulo that. We'll call the V's the core and the U's the straw part and the whole thing a nest. A union with the specified subsets. Here's an example, taking this n over 6n and adding just one more thing. I added one more 5. Instead of 5, I could have done any square free number not divisible by 2 or 3, by 2 and 3. And instead of 1, anything co-prime to that. The red things form a core, and the blue form the straw part. Now, what do I know about this? For a nest, every local lip function is lip. Also, the first Chekhov homology with coefficients in this covered by U sub I and V sub j is 0. And if you have a basic set and some cover of it by other basic sets, we can express our basic set as a union of an increasing sequence of nests made out from the sets from that cover. Basically, adding unused sets one by one, and then adding some more things that we like. Okay, what are some future goals of this theory? Number 1, prove the conjecture. In general, understand better the homology theory of the lip sheaf. Explore possible generalization. There are plenty. The theory is in infancy. We can first of all automatically go from n to z without 0. Everything pretty much works. Instead of z, we can consider Dedekind domains. We can also change the target. Mitun Vitil already changed the target to z adjoint 1/2. It would be even more interesting to change the target to include cyclotomic fields, because that would allow for arbitrary Dirichlet characters. Right now, the theory allows for real characters. Whenever you have sheaf of rings, it's good to consider sheaf of functions, so sheaf of modules over that sheaf of rings, like coherent sheaf in algebraic geometry, and more. Now, this third goal is kind of proof of concept thing. I'm not a fan of theories that just describe new things, create new questions, then gleefully resolve them. A good theory has to give back. And I'm sure quadratic reciprocity is somewhere there. I have ideas where, but I don't have it yet. Finally, goal number 4, find a good name for the theory. Arithmetic topology is already taken. There is a rather fancy theory using talk homology and subsuming class field theory that claims deep connection between Dedekind domains and three-dimensional topological manifolds. So we need something else. Okay, here are some references. And thank you very much for your attention.
Thank you, Alex. Are there questions? A lot of applause from Zoom land. Any questions from Zoom? All right, let's thank Alex again.
It's an interesting theory for sure.
What?
Thank you.
Was there a question coming in?
Well, there was a statement of interest in the theory.
Yeah, I should have said, whoever is interested, I need more people working on this.
All right. Thank you, Alex. Our next talk is in 3 minutes.
Is the name there, is that Kirch or is that like a Englishization of the name? Kirch? Because it's a German word.
The Kirch.
Kirch.
So that's a question for Alex.
So Alan Marshall Kirch, my understanding is he got his PhD in late 60s. He worked for many years at Macalester College. He did not do much publishing and did not publicize much his work. I reached out to see if he is still with us. I do not have the answer to that yet.
Where was he from originally?
So the question is, do you know where he was from originally?
I don't know. It seems like he possibly had a brother. So if you look at Saned, there are two Kirches, and both got PhD around the same time, late 60s. Both did not publish much.
All right. Thank you again, Alex.